This video is related to intermolecular force and understanding how intermolecular force is determined by polarity and the consequence of different elements having different intermolecular forces in regards to their physical properties. Okay, there's three types of intermolecular forces. There is dipole-dipole, there's H bonding, and there's London dispersion forces. And these three forces are forces of attraction between different molecules. Okay, so intermolecular forces are adjacent molecules, what force of attraction they have. Intramolecular forces are your actual bonds. Okay, so a nonpolar or polar or ionic bond is within the molecule. These are outside the molecules and how the molecules attract to one another, basically based on charge. Force of attraction that can happen between two different molecules is called a dipole-dipole attraction. We've already seen how molecules can have a separation of charge. When you have a polar covalent compound like HCl, which is shown here on your screen, what you have happen is the chlorine is more electronegative and it attracts electrons to itself to a greater extent than hydrogen. When it does that, the result is a partial negative charge existing on the chlorine side of the molecule and a partial positive charge being generated on the hydrogen side of the molecule. Once you have a whole bunch of hydrogen chloride in one location, what happens is those partial negatives and partial positives essentially attract one another. So a partial negative is going to attract a partial positive, and a partial positive is going to attract a partial negative. Okay? This is the force of attraction between polar covalent molecules. Because polar covalent molecules have partial charges in different locations, those partial charges attract one another. It's just like ionic bonding, right? Ionic bonding is the attraction between a positive and a negative charge on adjacent atoms. The difference here is just the magnitude of attraction. For an ionic compound, we have an entire electron contributing a negative charge, an entire proton contributing a positive charge. In this case, with the dipoles, you have a partial charge, which means it's a fraction of an overall full negative, so the attraction is less than it would be for an ionic bond. But it's still pretty big. Right? It's still pretty big. So what molecules exhibit dipole-dipole? Polar covalent compounds. Dipole-dipole molecules have a very high melting point and boiling point. Not as high as ionic, but they're higher than their nonpolar counterpart. Why? Remember that melting point and boiling point are about increasing the space between the molecules. That space is a byproduct of how well adjacent molecules attract one another. So molecules are being attracted to one another based on these partial charges. If you have a greater separation of charge, meaning a more polar molecule, you'll have a greater force of attraction. Essentially, this partial negative and partial positive will have a larger magnitude. Greater force of attraction means more force to overcome. Your next type of intermolecular force is called hydrogen bonding. I hate the name because it's not a bond, right? You have nonpolar covalent, polar covalent, and ionic bonds. This is an intermolecular force. It's a force of attraction between different molecules, so it isn't an actual bond. But biologists named it, so you just kind of go with it. The explanation for hydrogen bond is no different than the explanation for dipole-dipole. It's a force of attraction that's created because of partial charges ending up on polar covalent bonds. The reason it's its own category is, number one, the specific examples of hydrogen bonding are very large electronegativity differences, and number two, because of its biological implications. So hydrogen bonding is specifically in polar molecules that contain a hydrogen bonded to fluorine, oxygen, or nitrogen. If you have a polar covalent bond and you have hydrogen bonded to fluorine, oxygen, or nitrogen, you have hydrogen bonding. If you have hydrogen bonded to sulfur, for example, and it's polar, that would be a dipole-dipole force of attraction between molecules. This is only for hydrogen bonded to fluorine, oxygen, or nitrogen. They have very large electronegativity differences, which means a very strong force of attraction, very high melting points, very high boiling points. And again, the reason why it's its own category is actually because of how it affects your biology. Right? These are very common bonds within organic life, and the consequence is great for understanding how things interact. Your last intermolecular force is called the London dispersion force. These are for nonpolar molecules. Okay? Force of attraction is what gives us a solid or a liquid, because for solids and liquids, it's all about how well the molecules attract each other to whether it's a solid or a liquid. Solids attract a lot, liquids attract a little, gases don't at all. Nonpolar compounds don't have charges. Right? The electrons are shared equally. Now, if that were true, which it is true, but if that was all that was going on, we couldn't make nonpolar compounds into solids or liquids because they don't have any partial charges. Yet we see things like dry ice, liquid oxygen, liquid nitrogen. All three of those compounds are nonpolar, and they create solids and they create liquids. So how? Well, there's a guy called Fritz London who hypothesized that there's something called the London dispersion force happening. And what that has to do with is that dipoles must exist. Okay, if solids and liquids are created by an intermolecular force of partial charges, nonpolar molecules must have partial charges. And you're like, Ms. Lee, they don't have partial charge. I'm like, I know, but here's how it happens. Okay? Basically, electrons are moving all the time. And because they're moving all the time, potentially all of your electrons move to one side of your atom. For no other reason than they can. If all of your electrons group together, even for an instant in one location, you will create a partial negative charge. That is a teeny tiny dipole, and that teeny tiny dipole can cause attraction between adjacent molecules. Okay. Here's a pictorial representation that kind of helps you. Each molecule here is that oval. The green is the electrons. Normally, nonpolar, the green is evenly distributed. But for no other reason than they can, in one of the molecules, all the electrons group on one side. When that happens, they create a partial negative and a partial positive charge within the molecule. Now you have forces of charge that can potentially attract another molecule. That's what this says, teeny tiny dipoles. This alone doesn't produce exactly what we see, but what does produce it is something called an induced dipole. Now, this adjacent molecule that's right next to our molecule with tiny charges, all those electrons are hanging out. Right next to them now, they have a positive charge, which means all the electrons are saying, okay, great, I want that positive charge. And now we induce a dipole on the molecule next to it. Both now have partial negatives and partial positive charges. They can now attract and potentially create a liquid or a solid. Now, just as quickly as this happens, it undoes because the electrons are constantly moving. But because of the massive quantity of molecules we have, even if only a fraction of them are instantaneously creating dipoles and inducing dipoles, we can potentially create intermolecular forces. Now, they have to be really cold to make this happen because we need our molecules to be close to one another. As soon as you heat it up a little, they get too far apart and we can no longer induce dipoles. Within molecules that have London dispersion forces, the forces are very weak. They're instantaneous. They have a very low melting point and boiling point, and heavier, bigger molecules do this best because they have more electrons moving around, which cause a greater force of attraction. So that is basically the foundation of intermolecular force.